This will be a walkthrough of the AQA GCSE Physics 2023 Higher Tier Paper 1. Question 1. Figure 1 shows how the national grid connects a power station to consumers. Complete the sentences. So looking at our diagram, we've got a power station where our electricity will be generated, and then it is transferred to a transformer, which is connected to transmission cables, and then another transformer, which is then given to our consumers. Now, what is the transformer supposed to do? Any transformer is supposed to change the potential difference. However, coming from our power station, what we want to do is we want to increase the potential difference, and then going down to our homes, we want to decrease the potential difference. So transformer X will be the transformer that increases the potential difference, and we call that a step-up transformer. So that will cause the potential difference to increase. So that means that we know that this transformer here will be the step-down transformer. Transformer X causes the current to, well, if we have increased the potential difference, we then want our energy, electrical energy, to be transferred to our homes as quickly as possible. And that is a measure of the power, the energy that's transferred over time. However, when it's dealing with electrical power, we want to use the equation power equals current multiplied by potential difference. Now, if our potential difference has just increased due to the presence of our step-up transformer, then that would mean that the power would increase also. However, if our current is already high, then the problem will be is that the energy will be transferred and wasted as thermal energy from the transmission cables. And that's something that we don't want, because we want it to be quite efficient. So most, if not all, of our energy is going to the consumers. So what we want to do then, to make there be less power dissipated, is we want to decrease the current while we increase the potential difference, so the power remains high. So transformer X will cause the current to decrease. Use the physics equation sheet to answer the next two questions. 1.2. Which equation links current, power, and resistance? Tick one box. We just need to find the right equation that involves power, current, and resistance, and that will be power equals current squared multiplied by resistance. 1.3. A transmission cable has a power loss of 1.60 times 10 to the power 9 watts. The current in the cable is 2000 amps. Calculate the resistance of the cable. So we're using the equation that we've just identified above. So power equals current squared multiplied by R, resistance. In this question then, what are we given? We're given the power, so we should be plugging that into our equation. And we're given the current, so we should plug that into our equation also. And this now will guarantee us a mark, even if we rearrange incorrectly, because we have put the numbers in the equation in the correct way. So all we need to do to rearrange then would be 1.60 times 10 to the power 9 multiplied by 2000 squared, and that will equal our resistance. So putting that into our calculator generates an answer of 400 ohms. Use the physics equation sheet to answer the next two questions. Write down the equation which links efficiency, total energy input, and useful energy output. So again, looking at your equation sheet, finding the equation that involves efficiency, that'll be efficiency is equal to useful energy output divided by total energy input. (1.5) The total energy input to the national grid from one power station is 34.2 gigajoules. The national grid has an efficiency of 0.992. Calculate the useful energy output from this power station to consumers in gigajoules. So, for us to answer this question, we of course need to use the equation that we found above. So we will write that in a moment. But the next thing that we have to know is, what is this unit gigajoules? So the prefix of giga. Well, giga is equal to 10 to the power of 9. So that means if I've got 1 gigajoule, that is equal to 1 times 10 to the power of 9 joules. So our equation again to calculate efficiency is what we need to use. So once we do that, we just need to plug the numbers into our equation again in the right way, guarantee ourselves that mark. So the question has told us the efficiency, we know that that's 0.992, but it's also told us what the total energy input is. So what we can do then is, knowing this information about what the prefix giga means, is that we can turn our value into joules. So that would be 34.2 times 10 to the power of 9 joules. And we know that that's going to be equal to the useful energy output, so we need to find that. So again, we're just going to be rearranging now. So to find that useful energy output, it would be 0.992 multiplied by 34.2 times 10 to the power of 9. And that will give us an answer of 3.39 times 10 to the power of 10. And we know that that answer is going to be in joules right now, because our value here was in joules. So to get our answer in gigajoules, which is what they've asked us for, we would just need to divide this 3.39 times 10 to the power of 10 by 1 times 10 to the power of 9, which is what 1 gigajoule will be. And then that will give us a final answer now of 33.9 gigajoules. Question 2. Figure 2 shows the equipment a student used to determine the specific heat capacity of iron. The iron block the student used has 2 holes, one for the heater and one for the thermometer. So looking at our figure now, we've got a power supply connected to a joule meter. The joule meter by wires is connected to the iron block with a thermometer placed inside the iron block, and then we've got a stop clock to measure the time. 2.1. Before the power supply was switched on, the thermometer was used to measure the temperature of the iron block. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Suggest why. So the question is asking, why was the thermometer placed in the iron block before the power supply was turned on? So let's think, what's going to happen when the power supply is turned on? Well, that would eventually cause the heater to heat up, because energy is going to be supplied to it. And then that would in turn cause the iron block to heat up, which would cause there to be an increase in the reading on the thermometer, so an increase in the temperature. But why do we want thermometer to remain in the iron block first? Well, the thermometer itself is going to be recording the temperature, and it will be doing that constantly. No matter where the thermometer is, it will be recording the temperature. So if the thermometer is placed in a room, it will be recording the temperature of the room. Now, when you pick up an iron block, most of the time it will be cold. So that means then that the temperature of the iron block will not be the same as the temperature of the room that you're in. And the reason is because the iron block has a specific heat capacity, a certain amount of energy that's needed to raise 1 kilogram of that substance by 1 degree. So what that means then is that the thermometer would need placing the iron block then so that it can reach the temperature of the iron block first. Now that's important because you're going to be measuring the temperature change over the experiment. So you don't want the starting temperature to be the temperature of the room, you want the starting temperature to be the temperature of the block. So the reason is, so the thermometer can reach the temperature of the iron block. (2.2) Figure 3 shows how the temperature changed after the power supply was switched on. So let's analyze this graph then. The beginning, so 0 minutes, the temperature is 20. It remains there for about 2.5 minutes, and then it begins to increase gradually. And then there's a sharper increase all the way to 15 minutes. The energy transferred to the iron block between 5 and 10 minutes was 26,000 joules. The mass of the iron block was 2 kilograms. Calculate the specific heat capacity of iron. Use information from figure 3 and the physics equation sheet. 4 marks. So we have to be looking at our physics equation sheet and identifying the equation that involves specific heat capacity. So that equation would be the energy would be equal to mass multiplied by the specific heat capacity multiplied by the temperature change. So looking at the question now again, what values are given to us? Well, the energy transferred is given to us, so that's 26,000 joules. The mass of the iron block is given to us, so I know that's 2 kilograms. We need to calculate the specific heat capacity. So that means then that we are supposed to be given a temperature change somewhere. Now it's not written in this section here, so that means that we have to use the information from figure 3 as it tells us. Now remember that this energy value, 26,000, was between 5 and 10 minutes. So that means that we actually have to specifically find the temperature value at 5 minutes and the temperature value at 10 minutes, and then we'll be able to find the temperature change from there. So finding the temperature 5 minutes, reading along to our y-axis, that would be a value of 28 degrees. And then finding 10 minutes, that then be a reading of 54 degrees. So what that means that we can do then is subtract them, find the difference, 54 minus 28, and we know that will be 26, and then that will be our temperature change. So simplifying and then rearranging now, that would just mean that we would need to working out 26,000, because that's our energy transferred. And if we do 2 multiplied by 26, that will give us 52. And then that would equal our specific heat capacity. So putting that in a calculator, we're coming out with an answer of 500 joules per kilogram degrees Celsius. (2.3) The student repeated the investigation but wrapped insulation around the iron block. What effect will adding insulation have had on the investigation? Tick 2 boxes. So reading the question carefully now, they've asked us to tick 2 boxes. We should not be ticking 1. So there are 2 statements from this list that are correct. Now let's think about what's happening here. We've got an iron block. It's just been heated in the presence of the heater. But what they have done is they've wrapped insulation around the iron block. Now, what would typically happen is the energy from the heater would be transferred to the iron block, but then the iron block itself would transfer energy in the form of thermal energy to the surroundings. But because it's wrapped by this insulation now, it means that the energy that's transferred would actually be absorbed by the insulation. So that would mean that it would be difficult for the iron block to actually cool down, and it would remain hotter than it would without the insulation. So let's look through each of these statements and see which ones are supposed to be correct. So the first one says the calculated specific heat capacity will be more accurate. Well, let's think about our equation from our previous question now. We know that our equation is energy transferred equals mass multiplied by specific heat capacity multiplied by the temperature change. Now, what would happen if there was insulation? Well, the temperature would start to rise, but with the insulation wrapped around it, we would expect the temperature to not decrease as much or continue to increase fast. And the reason is because less is being transferred to the surroundings. So the temperature change would be closer to its true value, and that would mean that specific heat capacity, when you calculate it, will be closer to the true value. And that's what the word accurate means. And that should mean that the first statement is correct. Let's read the next statement. The iron block will transfer thermal energy to the surroundings at a lower rate. Well, as we were just explaining, the iron block is going to have insulation, so less thermal energy will be lost from it and go into the surroundings. So that correlates with the second statement. Question 3. Figure 4 shows an electrical circuit used to heat the windscreen of a car. Each resistor in the circuit represents a heating element. So looking at the circuit, we have a 12-volt battery, and then we have 6 resistors all in parallel to each other. 3.1. The 12-volt battery supplies direct potential difference. What is meant by direct potential difference? Well, there are 2 types of potential difference. There is direct, and then the other one is alternating. Now, thinking about the word alternating means constantly changing direction. Now remember that this is what is going to be supplied to homes through mains electricity. But direct potential difference would just be the opposite of that. That would then mean that the potential difference is not changing in its direction. So that's what we can write for our answer. Direction of the potential difference does not change. Now, also think about how a battery works. A battery has a positive terminus and a negative terminus. Now, if you were to take out a battery from a remote control, for example, and then turn it around and place it back into your remote control, you know that the remote control is not going to work because the battery has not been placed in the right way. Now, that means that the positive and the negative termini have been reversed. And this is also known as the polarity. So the other description for the direct potential difference means that the polarity does not change. Use the physics equation sheet to answer the next two questions. 3.2. Which equation links charge flow, energy, and potential difference? Tick one box. So finding the equation that involves charge and potential difference, you should notice that it will be the second one. Energy is equal to charge flow multiplied by potential difference. 3.3. Calculate the charge flow through the 12-volt battery when the battery transfers 5,010 joules of energy. So let's recall our equation again. Energy is equal to charge flow multiplied by potential difference. We need to calculate the charge flow. So that means that our 12 volts will be our potential difference. And that will be equal to 5,010, which is our energy. So rearranging that now, that'll be 5,010 divided by 12. And that gives us an answer of 417.5 coulombs. Question 3.4. Ice forms on the windscreen at a temperature of 0 degrees. The electrical circuit transfers 5,010 joules of energy to the ice. A mass of 0.015 kilograms of ice melts. Calculate the specific latent heat of fusion of water. Use the physics equation sheet. So finding the correct equation right now, that includes specific latent heat of fusion. So that will be energy is equal to specific latent heat of fusion multiplied by mass. So going through our question again, let's identify what values we need. So the electrical circuit transfers 5,010 joules of energy. So that will be our energy, which we can plug into our equation now. A mass of 0.015 kilograms of ice melts. So our mass would be 0.015. So that means that we need to rearrange the equation to find the specific latent heat of fusion. So that would be 5,010 divided by 0.015. And that will generate an answer of 334,000 joules per kilogram. Question 3.5. The electrical circuit was left switched on while the ice changed from a solid to a liquid and increased in temperature to 5 degrees Celsius. Explain the changes in the arrangement and movement of the particles as the ice melted and the temperature increased to 5 degrees Celsius. 6 marks. So the ice is changing its state from a solid to a liquid. We need to talk about the arrangement first. So thinking about the arrangement of particles in a solid, what would we expect to find? A regular pattern. They're fixed positions, not moving but vibrating. Particles are touching each other. They have low energy, but when the temperature increases and then it turns into a liquid, you'd expect that regular pattern to be disrupted. So now the particles are more in a random arrangement. You'd expect them to be moving, so you'd expect them to have a lot more energy. But what we need to think about is the types of energy that we would expect these particles to have in a liquid. Now, in a solid, as we said that they have low energy, the specific type of energy that they'd have, which would be lower, would be kinetic energy. So kinetic energy would be lower in a solid, but it would be higher in a liquid. But remember that when the particles start to move, more of them would be moving upwards in a liquid. So that means not only would they have higher kinetic energy in a liquid, they also have higher potential energy in a liquid. Now, what is that type of energy called, which is a combination of kinetic and potential? It's the internal energy. So in a liquid, the particles would have greater internal energy. So let's try and put all of that together now, formulate our answer to get 6 marks. So in a solid, the particles have a regular pattern. And they're vibrating at fixed positions. When the temperature increases, particles gain kinetic energy and begin to move faster. In a liquid now, we can start to talk about the particles have a random arrangement. And are able to move freely. Their kinetic and potential energy increases. This is known as the internal energy. Now, what we can think about lastly is our graph, which shows a change of state. So on our y-axis, we've got a temperature. And then you can think of our x-axis as the time, the progress. At the beginning, you get an increase in the temperature. But then it remains constant. And then that happens again. increase in temperature, and remains constant again. So where does the change of state occur? The change of state occurs at these horizontal points on our curve. So when there is a change of state, the temperature actually remains constant. So in this case, where the ice is melting, the temperature will remain constant. So we could just throw that in the middle. Question 4. A remote village in the UK uses an hydroelectric generator to provide electricity. In one day, 2.5 million kilograms of water passes through the hydroelectric generator. A change in gravitational potential energy of the water is 367.5 megajoules. The gravitational field strength is 9.8 newtons per kilogram. Calculate the mean change in vertical height of the water as it moves through the hydroelectric generator. Use the physics equation sheet, 4 marks. So, for this question now, we need to use another equation. So let's look at the values that are underlined and let's see what equation we could use. There's a mass here, 2.5 million. There's a change in gravitational potential energy. So that is energy. We've got gravitational field strength, that's given to us also. And it's asking us to calculate the mean change in vertical height. So going through our equation sheet, the equation that would be most appropriate here would be change in energy is equal to mass multiplied by gravitational field strength multiplied by height. So let's plug in the numbers that are given to us in the question. Our change in energy is 367.5 megajoules. So again, similar to our previous question, we've got a prefix in front of joules. It's not giga this time, it's mega. So mega is equal to a million. That would be times 10 to the power of 6. So that means if I've got 1 megajoule, that would be equivalent to 1 million joule. So what we'll do is the same thing that we did as previous. We're going to convert the value to joules. So that will be 367.5 times 10 to the power of 6. And that will be equal to our mass, which is 2.5 million, multiplied by 9.8, so our gravitational field strength, and multiplied by the height, which we need to find. So again, we're rearranging the equation here. So rearranging the equation, 367.5 times 10 to the power 6 divided by 2.5 million multiplied by 9.8. Plugging that into our calculator, it generates a value of 15 meters as our final answer. Question 4.2. The generator transfers 3 kilowatts of electrical power. Calculate the time taken for the generator to transfer 2.16 times 10 to the power 7 joules of energy. Use the physics equation sheet. Give your answer in standard form. 5 marks. So again, we're looking for an equation, but involves power, energy, and time taken. So that equation would be power equals energy divided by time. So another question with the prefix. So the prefix is kilo. Kilo is 1,000. So 1 kilowatt will be equal to 1,000 watts. So what we can do is convert that 3 kilowatts to watts. So that would be 3,000 watts. And then we can put in our value for energy, 2.16 times 10 to the power 7. And then that will be divided by the time. So rearranging this now, that would then mean that to find our time, we would need to 2.16 times 10 to the power 7 divided by 3,000. Doing that, we get a value of 7,200, and that would be in seconds. But they've reminded us one more time that we need to have our answer in standard form. So remember that the rules for standard form are you need to have a number between 1 and 9.9. So in this case then, our value would be 7.2. But we need to take into account the zeros. So where would our decimal place be? 1, 2, 3. So 7.2 times 10 to the power 3 seconds is our final answer. Question 4.3. Figure 5 shows how the power output of the generator varied during 1 year. So let's analyze our figure. We've got the month on the x-axis. We've got the power output of the generator in kilowatts on the y-axis. The months in the year are given, so January to December. And we can see from January, we've got a power output of 5 kilowatts, which appears to be the highest. And then as the months progress, it appears to decrease, going as far down at July, where it's lowest. And then from August to December, it's increasing again. A solar power system is installed in the remote village in addition to the hydroelectric generator. Explain why this improves the reliability of the electricity supply to the village. Use information from figure 5. So, let's focus on this first sentence here. Solar power system. When we're thinking about solar power, it's to do with absorbing of light. So what will happen is the light energy that is coming from a light source, for example the sun, will be absorbed by the solar panel, and then it's used to generate electricity. The hydroelectric generator works through hydroelectricity, and that is the principle of falling water. So using the energy from falling water, that is used to generate electricity. So why would both of these two methods of generating electricity improve their reliability? Well, let's think about if one was only present. So imagine that the hydroelectric generator was not there, and it's only the solar power. Well, as we've identified, it only works on the principle of light. So you need light to be present for there to be electricity generated. Well, from our figure, we've got different months of the year. So we have to think, when would the light intensity be its highest? We would expect the light intensity to be highest in the summer months, which would be May, June, July, August. But what does that mean for the rest of the year now, when it's not as intense in terms of the light? That would mean then that the power output would be lower. So that means the electricity would not be supplied to the village as much. Let's do the opposite. If there was no solar power system, but there was a hydroelectric generator only, well, as I said, it works on the principle of falling water. What would be an example of falling water? That would be rain. So when would we expect there to be rain? Well, most of the time it would be occurring in the spring season, and that would fall around March, April. So the other times of the year, you would get less rain, so less falling water, so there would be less power output and then less electricity supplied. So the combination of having both these two sources of generating electricity would mean then that you would sustain the power output relatively high, so that would also then mean that a constant supply of electricity will be generated and supplied to homes. So for us to gain our marks now, what you would need to do is you need to refer to both solar power and hydroelectricity. So what we can say first then, because as we use the information from the figure, we can focus on the summer months, and we can say in the summer, power output would be greater from solar power and lower from hydroelectric. Now remember what we've done. We've used the information from the figure. We've mentioned the summer. If you want to be specific, we can say from May to August. But then our second mark needs to be how this is going to improve the reliability. Now look what's happened here from our graph. Remember that this is just from the generator that's hydroelectric. So when the solar power is installed, we would expect this power output to be much, much higher. So what we can say then is there will be less variation in the power output. So that would just generally mean that it would be more constant, and that would improve the reliability. Question 5. Some isotopes emit nuclear radiation. Carbon-14 and carbon-12 are isotopes of carbon. Compare the structure of an atom of carbon-14 with the structure of an atom of carbon-12. Now remember, this will be a physics exam, so you won't be supplied with the periodic table. So what you need to do is you need to make sure that you understand what this number means next to an element. These numbers represent the mass number. And the mass number means the number of protons and neutrons in an atom. But remember the definition of an isotope. The atoms are the same element with different numbers of neutrons. So the only way that these two isotopes vary is due to the numbers of neutrons. So that can be our first mark. They have different numbers of neutrons. Now remember then that these are atoms of the same element, both carbon. If they're both carbon, then that means that their atomic number is the same. And the atomic number means the number of protons in an atom. So remember that we're comparing, and the command word compare means to give similarities and to give differences. So think about what we've done already. We've given a difference. They have different numbers of neutrons. Carbon-14 would then actually have 2 more neutrons compared to carbon-12. We could state that if we wanted to. But what are the similarities here now? The similarities will be that they have the same number of protons. But what else does the atomic number tell us? It tells us the number of electrons also. Remember that for an atom, they should have equal amounts of positive and negative charge. So that would then mean that this number of electrons would also be the same. (5.2) Carbon-14 is a radioactive isotope. Carbon-14 has a half-life of 5,700 years. What does a half-life of 5,700 years mean? So we need to know the definition of half-life. That's really what the question is asking us. So the definition of half-life is the time it takes for the radioactive nuclei in a sample to half. So in this case then, it takes 5,700 years for the radioactive nuclei in carbon-14 to half. So let's write that. Now remember, it doesn't matter what nuclei it is, it's not just going to be carbon-14, but that definition would always apply. Table 1 gives the half-life of some other radioactive isotopes. So 4 isotopes given to us and their half-lives. 5.3. A sample of fluorine-17 has an activity that is 1/4 of its original activity. Calculate the age of the sample of fluorine-17. So the activity is 1/4 of its original activity. This is the key point here, 1/4. Now, if we think about a typical graph that involves half-life, on our x-axis it would have the time, and on the y-axis it usually have the count rate or activity. And they typically have a graph which is something like this, a curve. So what it's telling us now from the table is that the time that it takes for the nuclei in fluorine-17 to half, that's radioactive, it would take 64.37 seconds. So we could put that there, and that would be the half-life. Remember, it's telling us that that's 1/4 of its original activity. So that's not the same as 1/2. That's actually a half multiplied by a half. So that's equal to 1/4. So if one half-life takes 64.37, and that would be this, then we would need to drop it by another half to get the age of the sample of fluorine-17. So what that would actually mean then is you need to go down by another half. So let's imagine that this now is our next half. Now remember that this half-life value, 64.37, won't change. So what we would need to do is double 64.37 to get our actual age of the sample. So essentially what you actually found out is 2 half-lives. So it would be 64.37 multiplied by 2. There are 2 half-lives, and that would be 128.74. 5.4. All of the isotopes in Table 1 emit beta radiation. Explain which isotope would cause the biggest risk to a person's health based only on the half-life of each isotope. So what we're doing then is we're only focusing and using the information in the table to try and work out our answer. So which one of these would be the most dangerous? Well, again, let's focus on the definition of half-life. The time it takes for your radioactive nuclei in a sample to half. Now, what that's really saying then is that whenever your radioactive nuclei start to decay, so let's use this dark circle as decayed nuclei now, they will be emitting beta radiation. And that is not good for a person. So realistically, the quicker that it takes for the nuclei to decay, the more dangerous it's going to be. So going back to the table then, we want to find which of these isotopes is going to really decay the quickest. And decaying the quickest means the shortest half-life. So we can see that nitrogen-18 has got a half-life of 0.62 seconds. So half of the radioactive nuclei in nitrogen-18 would decay in 0.62 seconds. So that has to be the most dangerous. So we should get 1 mark for mentioning the isotope, nitrogen-18 in this case. And what's our reasoning? So our reasoning would be the fact that they would be decaying fastest. Remember, we use this graph here to try and help us understand how half-life works some more. So then that would mean that the activity of the nitrogen-18 would be the highest. So we should state that next. Highest activity for nitrogen-18. Now, what's the risk to a person? Well, how do these radiation work? Well, when they're emitted from nuclei that's unstable, they can be absorbed by a person. So what would be the problem in this case then, if nitrogen 18 has got this highest activity? That means that it's going to have the greatest dose absorbed. Question 5.5. People who work in the nuclear power industry need to be aware of irradiation and contamination. Describe the difference between irradiation and contamination. So, a person can either come into contact with an object that is radioactive, or they can be exposed to an object which emits radiation. And that's the difference between these two terms here. So when a person is coming into contact with a radioactive material, that's contamination. When a person is exposed to radiation, that is irradiation. So let's just make that clear. Irradiation is the exposure of an object to radiation. But contamination is the presence of radioactive material on an object. Five point six. Give one health risk to a person working close to a source of nuclear radiation. Well, one of the common issues with someone that's been exposed to radiation is going to be cancer. If you know your history and the Chernobyl accident, which occurred in 1986, many people suffered from cancer and died as a result. And also the children from those that were exposed to radiation, irradiated, were having further health issues such as issues born without limbs, and then increasing the risk of them himself developing cancer. Question 5.7. Workers in nuclear power stations are monitored to check the radiation they emit. A worker stands 1 centimeter away from a radiation detector. The amount of radiation the worker emits is recorded. Explain why the worker needs to stand close to the radiation detector. So, if the detector is placed down and a person stands next to this detector and they're emitting radiation, it'll be picked up by the detector. But we must remember that there's different types of radiation and they have different properties. So the 3 types of radiation are alpha, beta, and gamma. Now the properties in this case that we are interested in is its range in air. We're not interested in their penetrating power. We're interested in their range in air. How far do they travel? Now remember that gamma is just a wave. It's an electromagnetic wave. So it's going to have a very, very high range in air. Beta radiation is a high-speed electron. So it's going to have a decent range in air, but it's going to be a bit lower than that of gamma. Remember that alpha radiation is a helium nucleus, 2 protons and 2 neutrons. So because that's quite a large molecule in comparison to the other two, it's going to have quite a short range in air. So very, very short distance it can travel. Remember that the question told us that the worker needs to stand 1 centimeter away from the radiation detector. Now, what would that allow the detector to pick up? It would allow the detector to pick up alpha radiation because it's got a short range in air. So what we would need to say then is we need to make it clear that we know that there may be some alpha radiation that may be emitted. And the property, again, that we are interested in is that it has a short range in air. .8 Workers in the nuclear power industry are exposed to nuclear radiation. Pilots on aircraft are exposed to cosmic radiation from space. Daily dose caused by working in a nuclear power station is 0.00050 millisieverts. The hourly dose from cosmic rays to a pilot when flying is 0.0030 millisieverts. Calculate the number of days it takes for a nuclear power station worker to receive the same dose as a pilot flying for 24 hours. So, the time period that they've told us is 24 hours. They've told us a daily dose and an hourly dose. We need to get a comparison between them, which is the same. So, the first thing that we would need to do now is we would need to take this value for a person that is flying and scale it so it reaches how long a day is. So remember that one day is 24 hours. So we would need to take that value 0.0030 and multiply that by 24 so we know how much they would be exposed to in 24 hours. So just multiplying the values together to come out with a value of 0.072 millisieverts. But remember that our daily dose from a person working a power station is going to be 0.00050 millisieverts. So what we would need to now figure out then is how long would it take for them to get the same dose. So what we need to do then is find out how many more days that would take. So you can just take our value that we just calculated, 0.072, divide that by 0.0050, and we'd come out with an answer of 144 days.